is going to be our last but not least talk. Prakash Surya, who probably everyone here knows. As Matt mentioned, he has implemented the automated testing for OpenZFS. So today he's going to present about performance improvements to the ZFS intent log. So please welcome Prakash.
Cool. So yeah, I'm Prakash. I'm going to talk about my ZIL performance improvements. So here's a brief overview of what I plan to discuss. It's broken up into roughly 3 parts. First, I'll give some background and discuss what the ZIL is, how it's used, and how it works. Then I'll get into the problem I set out to fix, how I fixed it, and provide some details on how I did that. And then lastly, I'll show off some graphs and results of my work. So with that out of the way, let's get started. First off, what is a ZIL? ZIL stands for ZFS intent log. It's a mechanism that's responsible for logging synchronous operations to disk. The operations that get logged are logical operations, such as ZFS create, remove, etc. This does not include non-modifying operations, such as ZFS read, seek, etc. The data that gets logged is simply the fact that the logical operation occurred. For example, for ZFS remove, it's only the name of the object to remove and the object ID of the directory from which that name will be removed. It's not which blocks on disk would change due to that removal. The ZIL is almost always used. Whenever any of these logged operations occur, they're inserted into the ZIL's in-memory list of operations. These operations are often called ITXs, or intent log transactions. When the ZIL is called, the ITXs tracked by the in-memory ZIL are written to disk when ZIL commit is called. The caveat to all of this being, none of this occurs if the dataset is configured with sync equals disabled. If sync equals disabled, ITXs aren't tracked in memory, nor are they written to disk. Since I often see the ZIL and slog terms used incorrectly, I wanted to briefly address this. Slog stands for separate log device. The ZIL and slog are different in that the ZIL is a mechanism for issuing writes to disk, and the slog may be the disk that the writes are issued to. With that said, an slog is not necessary. By default, ZIL writes will go to the main pool's disks, but an slog can be used to try and improve the latency of ZIL writes if the main pool's VDEVs are deemed too slow. So why exactly does a ZIL exist in the first place? Well, writes in ZFS are write back. What that means is data is first modified and stored in memory in the DMU layer, and then later at some point the data is written to disk via SPA sync. The problem is SPA sync can take tens of seconds or more to write out this data. It's unacceptable for all sync writes to take tens of seconds to complete. Further, writes in ZFS often cause more writes to occur. For example, a single file write modifying a single block of user data will then cause indirect blocks to also be modified and written. The ZIL allows this write amplification effect to be mitigated. Essentially, the ZIL exists as a performance optimization to provide synchronous semantics to applications faster than what could be achieved with SPA sync alone. While correctness could be achieved without the ZIL, performance would be unreasonably bad, which makes it a necessity. Before I jump into the next section, I wanted to quickly go over the on-disk format of the ZIL. Each ZFS dataset maintains its own unique ZIL on disk. Each of these ZILs is a singly linked list of ZIL blocks, or as they're also called, LWB, which stands for log write block. As one can see here, the Uber block has a pointer to the MOS, which then has pointers to each dataset in the pool, and each of these datasets has a pointer to its own ZIL header. Each ZIL header then points to an LWB, and that block points to the next block in the list. Now let's get into how the ZIL is used. The ZIL is used by the ZFS POSIX layer, or ZPL for short. The ZPL interacts with the ZIL in 2 phases. First, it uses ZIL ITX assign, which causes the ZIL to log the fact that an operation is occurring. Then it uses ZIL commit, and this tells the ZIL to write out these log records to disk. Let's look at ZFS write as an example of this. ZFS write will call ZFS log write. ZFS log write will then call ZIL ITX create, which will create the ITX structure in RAM. Then it'll call ZIL ITX assign, which will insert that ITX into the ZIL's in-memory state. Finally, if this is a sync write, ZFS write will then call ZIL commit, which will cause the ITX to get written to disk. Now let's look at ZFS fsync as another example. Fsync doesn't create any new modifications. Instead, it simply ensures any previous operations are written to disk before it returns. Thus, ZFS fsync doesn't call ZIL ITX create, nor does it call ZIL ITX assign. Instead, it only calls ZIL commit. Calling ZIL commit will ensure all previous operations are written to disk before fsync returns. The parameters of ZIL commit are such that the caller will pass in enough information to uniquely identify an object whose data is to be committed, and the contract the ZIL maintains with the caller is all operations relevant to the object specified will be persistent on disk by the time ZIL commit returns. By relevant, it means all operations that would modify that object, and by persistent, it means the operations are written to disk and the disks used for those writes are flushed. Further, we must issue the disk flush after the write's complete. Lastly, the interface for ZIL commit doesn't allow the caller to specify which operations they care about. Thus, ZIL commit must write all operations for a given object, even if the caller only cares about a subset of those operations. For example, if there's multiple threads writing to the same file but at different offsets, all offsets must be written to disk before ZIL commit returns, even if the calling thread only cares about one of those offsets. So how does the ZIL accomplish this? Well, as I alluded to previously, the ZIL maintains an in-memory list of ITXs that have occurred, but haven't yet been written to disk. This list is maintained via the ITXG structure in the ZIL, and each ITXG structure contains the following: a single list of all sync operations that have occurred for all objects in the dataset, plus per object list of async operations for each object modified. Here's what this might look like. In this example, the ITXG's sync list has 2 ITXs in it, each of which could map to an operation for any object in the dataset. And then a list of async operations that occurred for object A, and a list of async operations that occurred for object B. When ZIL commit is called, how do these ITXs get written out to disk? Well, first we must determine which of these ITXs are relevant, and then we must move these relevant ITXs to a new list called the commit list. Here we have the same ITX list as before, except now we also show an empty commit list at the bottom. Also, let's presume ZIL commit is being called for object B. The first step is to move all of object B's async ITXs to the sync list. So we select the ITXs and move them. Next, we move the entire contents of the sync list to the commit list. Additionally, it's worth pointing out, the point of the commit list is so we have a list of ITXs to write out that will not be modified by any concurrent ZPL activity. As new ZPL operations occur, the sync list may change. For example, operations may be added to it, but the commit list will remain the same. Now that we have a list of ITXs to be written out, it's time to actually issue them to disk. We do this by iterating over all of the ITXs in the commit list. Then for each ITX, we attempt to copy it into the currently open ZIL block. If there is insufficient space in the block, then we allocate a new block and issue the old one to disk. Lastly, after all ITXs are copied into LWBs, we issue the last open block to disk, allocating the next open block in the process. So here's what I mean. Given the commit list from before and LWB1 as a currently open ZIL block, we select the first ITX in the list. So here we select ITX S1 and copy this into the block's buffer. This block will remain open as denoted by the dotted line, since it may also be used for the next ITX in the list. So now we move on to the next ITX, ITX S2. This one doesn't quite fit in the currently open ZIL block. As you can see, it doesn't fit in LWB1 here. So we must allocate a new block and issue the current one to disk. Here, LWB1 now has a solid line to indicate it's been issued to disk, and LWB2 has a dashed line to indicate it's a new OpenZIL block. Further, LWB1 maintains a pointer to LWB2 on disk, and that's the singly linked list relationship that I mentioned earlier. Now we can go back to processing the commit list. So we go back to ITX S2 and copy the ITX into the new LWB, into LWB2, the open LWB. Finally, we reach the last ITX in the list, ITX B1. Since this fits into LWB2, it's copied directly into place. And at this point, the commit list is empty. So we issue LWB2 to disk, allocating the next open block in the process. So here, LWB1 and 2 have been issued to disk. As we can see, they have the solid line, and then LWB3 has a dashed line to indicate it's now the new OpenZIL block. And this block will be used when writing out the next batch of ITXs. Now, after we've issued all ZIL blocks to disk, we must wait for them to complete. The blocks can complete in any order. Here, LWB2 completes first, and then LWB1. At this point, all blocks have completed, so it's time to issue a disk flush to the VDEVs involved. So we flush the VDEVs, and once those complete, we can notify any waiting threads, letting them know that their data is safe on disk. So now let's dive into the problem with all of this. So the main issues can be summarized into the following 3 points. First, ITXs are grouped and written in batches, where the commit list constitutes a batch, and the batch size is proportional to the sync workload on the entire system. Next, threads waiting for ZIL commit to complete are only notified when all ZIL blocks in a given batch complete. So if a given batch is large, that means ZIL commit must wait for all of those blocks to complete, even if the caller only cares about a small percentage of the data in that batch. And lastly, only a single batch can be processed and written out at any given time. Here's an example of what this ends up looking like. This is a timeline of the disk activity of an example pool. What can be seen here is blocks A through E, that first green batch. Blocks A through E are all written in the first batch, but the disk activity is slightly uneven. While disks 2, 3, and 4 only receive a single ZIL block to write, disk 1 receives 2 blocks, as you can see. Thus, disks 2, 3, and 4 complete their writes and then remain idle, while disk 1 finishes its work. This idle time is due to the fact that only a single batch can be processed at a time, which leads to inefficient usage of the storage. For example, blocks F, G, and H, as shown in the yellow batch just after that first green one, blocks F, G, and H could have been issued to disks 2, 3, and 4, filling this idle time, but the batching mechanism prevents this. Another issue is the fact that waiting threads will only be notified once all blocks in a batch complete. For example, if a thread was waiting on data to be written by block A, written by disk 1 up there, it would also have to wait for block E to be written as well, also written by disk 1. This unnecessarily increases the latency of ZIL commit, and in this case, potentially doubling it. The solution is somewhat obvious. Let's just remove this concept of batches. Rather than waiting for the current batch to complete, we should issue new ZIL blocks to disk immediately as soon as they can be written out. Further, rather than waiting for a batch to complete before notifying threads, these threads should be notified immediately when their data is safe on disk. If we did that, then we could go from this diagram, which I showed earlier, to this one, where all disks in the pool are saturated and threads are notified as soon as each individual block completes. As this diagram illustrates, we'd be able to service the same number of ZIL blocks in nearly half the time, potentially doubling our IOPS. And this is without changing a single thing about the workload, nor the underlying storage characteristics. So how is this accomplished? The bulk of the changes revolve around three things: changing how ZIL blocks are issued to disk, changing when the flush commands are sent, and changing how we notify waiting threads. Previously, this was a sequential three-step process. Step 1 would consist of creating the ZIL blocks, issuing these to disk, and then waiting for the I/O for all of the blocks to complete. Next, after the blocks completed, step 2 would consist of issuing the flush to each VDEV and then waiting for those flushes to complete. And finally, after all those flushes completed, the ZIL CV would be signaled to notify any waiting threads. All threads that called ZIL commit would be waiting on the CV, so this was a mechanism to let them know that their data is safe on disk. All three of these steps would consist of a single batch. After one batch completes, another would start up, and another. This three-step process would repeat as long as a workload would allow, as long as you have synchronous operations and sync writes going on the system. Now the process is entirely different and heavily leverages the ZIO infrastructure. Instead of a single root ZIO for an entire batch of blocks, each block now has its own unique root ZIO. Each root will eventually have two children, a write ZIO containing the ITX data to be written, and a flush ZIO that is issued after the write completes. Since these are each child ZIOs, the root cannot complete until both the write and the flush complete. This is enforced by the pre-existing ZIO parent semantics, so I didn't have to change any of that. I just got it for free by using ZIOs. Further, the root ZIO of the previous block will also be a child of the next block. For example, here, LWB1 is a child of LWB2. This ensures LWB root ZIOs complete in the correct order, again leveraging ZIO dependencies to achieve this. Finally, each LWB maintains a list of CVs where each CV on this list maps to a single thread that called ZIL commit. Rather than all threads using a single CV, we now have a CV per thread. Then, when the root ZIO for any ZIL block completes, each CV in the block's list is signaled, notifying the waiting threads that their data is safe on disk. Let's walk through an example of what this looks like. First, the LWB structure in the root ZIO is created. Initially, the list of CVs will be empty, but as ITXs are copied into the block's buffer, it will begin to accumulate a list of threads waiting on it. Next, when the block's buffer is full, its write will be issued to disk. Then, when that write completes, the flush will be issued. When the flush completes, and since the ZIL block doesn't point to any previous block, this will allow the root I/O for this specific block to complete, at which point each CV in the block's list will be signaled. This same process will occur for the next block and the next. At this point, though, it's important to note the sequence of events doesn't have to occur in this specific order. For example, it's possible for block 2 to issue its write before the write for block 1 completes. In this case, the write for block 1 would have been issued, and then the write for block 2, even though block 1's write was still being serviced by the disk. Previously, this would have been prevented due to the batching mechanism. The write for block 2 could not have been issued to disk until the write for block 1 was complete. The same goes for the write for block 3. We can also issue block 3 to disk before 2 and 1 complete. It's even possible for the writes of block 2 and 3 to complete before the write of block 1. If this happens, though, the root of block 2 and 3 will still be blocked, waiting for block 1 to complete. Thus, even if the flushes were issued and completed for blocks 2 and 3, their CVs would not get signaled yet. As soon as the write for block 1 completes, the flush would be issued, and once block 1's flush completes, then all three blocks would complete simultaneously, and the CVs for all of these blocks would be notified. So, while before this process was very sequential, Now it's completely driven by the incoming sync workload and disk completion events. ZIL blocks are created and issued whenever there's data to write, and waiting threads are notified whenever those writes complete. Before jumping into the performance results, I wanted to quickly talk about how we determine when to issue a ZIL block to disk. If you remember from earlier in the talk, we build up these blocks by iterating over the commit list and copying each ITX into one of the LWB buffers. Previously, once we reached the end of the commit list, in essence, the end of a batch, we would issue the last LWB to disk. Now that we're batchless, we don't necessarily want to do that. If we reach the end of the commit list, but there's still buffer space available in the current block, for example, we could have a 128K ZIL block with only a single AK write in it, then we actually want to delay issuing that block just in case new ITXs are generated that would still fit in that ZIL block. This way, we can write out more ITXs using fewer IOPS. The problem is we have no way to predict the future here. We don't know for sure if more ITXs will be generated. Thus, if we wait for future ITXs but none are generated, we're adding additional latency to the current LWB for no benefit. But if we don't wait at all and additional ITXs are generated, we could end up using more IOPS than we need to and potentially degrade performance by saturating the disk. The solution we implemented is a ZIL block may be delayed up to 5% the latency of the last completed ZIL block. So for example, if the last block took 5 milliseconds.
Okay, I just want to make sure that the slides are still working.
Yeah, it's the same one. So if the last block took 5 milliseconds to be serviced by the storage, then the next block will wait a maximum of 250 microseconds. If it's filled within that 250 microseconds, it'll be issued to disk immediately. So like here, if LWB2 might still have some space in it, so it'll probably wait here, right? It'll wait for the timeout. So if it's not filled, it'll time out after 250 microseconds and be issued to disk partially filled. But if there are more ITXs in the commit list, LWB2 could be filled and issued to disk immediately without waiting that full 250 microseconds. And for those wondering, 5% is a default. And not that I recommend doing this, but it can be changed using a new tunable if you want to wait some other percentage. Finally, let's go over the results of the performance tests that were used to verify this. I used 2 different FIO workloads to verify. For this workload, each FIO thread was submitting sync writes as fast as it could, and I measured the total number of IOPS that were achieved across all FIO threads. And I varied the number of FIO threads from 2 to 1024. This graph shows the percentage difference in IOPS between Illumos with my changes and Illumos without my changes. The dashed line at the bottom is just a visual aid showing to highlight where a 0% difference would be. So anything above that line is improvement. And on average, I measured an 83% increase in IOPS with my changes. The dotted line in the middle is another visual aid simply to show where exactly 83% improvement is in relation to the actual measurements taken. And additionally, this Z-pool used for this graph consisted of 8 traditional spinning drives. I also ran the same workload on a Z-pool consisting of 8 SSDs. When running on SSDs, the improvement isn't as dramatic, but I was still able to measure a 48% improvement on average. Again, the same visual aids are here. The dashed line at the bottom, anything above it is improvement. And then the dotted line kind of in the middle-ish is the average to show a 48%. 48% improvement. The second workload tested was again using FIO. But this time, each FIO thread would attempt to issue a maximum of 64 sync writes per second. Thus, the number of IOPS was constant with and without my changes, but the latency of each sync write was still improved. Since now we're measuring latency rather than IOPS, any value below the dashed line is improvement. The dashed line still showing 0% change. When running this test on my 8 spinning disk pool, I measured the latency of each sync write to decrease by an average of 27%. Also worth noting, the IOPS began to diverge at thread counts greater than 64, where my new code started doing more IOPS than the old code. So I removed those data points to keep the comparison fair. There was still improvement, but I didn't think it was fair to show that. And lastly, I ran that same workload with a constant FIO sync writes per second on my 8 SSD system. The IOPS were the same for all thread counts on this pool, so I didn't have to remove any data points. And here I measured the latency to decrease by an average of 16% on this system. Here's some more details about the test that I ran. Not going to spend much time here, and just for posterities, there's another link to more information. And with that, that's all I got. Questions?
Did you do any performance testing with mixed workloads involving some section of sync writes instead of purely sync writes?
I ran testing, but I didn't. Did I run any performance testing with a mixed workload of sync and async writes, or any other mixture of stuff? I ran testing, but I didn't measure like the performance difference of that, just simply because I wasn't really sure how to get a baseline and how to compare when, I really wasn't sure what was important to test, because the test matrix kind of expands exponentially with all of these different variables. So I ran a test for like 24 hours, just let it do whatever the hell it wanted to do with a mixture of reads, writes, sync, async, just to make sure it didn't blow up, but I didn't really measure the performance differences there.
Is there any difference if you're using the slogs in the configuration?
There shouldn't be. So my changes were all, is there any difference between using an slog? So all of my changes were above that layer, so I didn't touch any of the allocation code. I just touched how it is issued and tried to remove the batching and the wake-ups and that sort of thing. So I would expect slog to also have improvements, but as I showed with my SSD testing, the improvement isn't as great there, and there's still some more things that we could improve on to make it better for really low latency drives, and that was kind of the issue that I saw with the SSDs, is just really low latency drives. The current algorithm, it's good enough. So
I'm curious what the number of drives makes a difference.
I think it will improve with the number of drives based on the theory, and I did run some tests on Linux with a bunch of drives because Brian Bellendorf gave me a box to test with, and I saw the same improvements with lots of drives, the same percentage improvement. The graphs were mostly the same, so yeah.
Do you have a feeling for how often your little 5% delay was able to catch a few more records?
Do I have a feeling for if my 5% delay was able to catch like ITXs and improve the performance, right? It definitely did, because that could be either due to my early code being buggy and just not correct, or the delay. But what I did know is that early on I didn't have any delay, so every time we reached the end of the commit list, it would issue that LWB to disk immediately. And what I saw was because of the changes that I made to how the blocks are like how the commit list is built up and how there's no batching. The commit list usually was like 1 or 2 ITXs, or a very small number of ITXs each time it was traversed. So we would get 2 ITXs into a LWB, and then we would issue it to disk immediately. So what happened is I was seeing, instead of using large 128K LWBs using the maximum size, I would see a lot of like 16K LWBs filled with much smaller ITXs. So it's hard for me to say how much it helped because I didn't try and do before and after with and without the delay with my final code. But early on, performance was terrible until I added that delay. So it really was critical to not only pack ITXs into the LWBs, but make sure that the algorithm was using as large of an LWB size as possible.
I thought that, when you were doing the max IOPS test, I thought that it was like however many threads you had, that was like how many ITXs would go into the block without when you didn't have the delay. Wasn't there something weird like that where it was related to the number of threads?
Say that again.
Like the number of threads would determine how many ITXs went into the block.
Yeah. So
Or like it would alternate between like 2 and then it would like if it 8 threads, it'd be like 1 7 1 7 1 7 or some weird thing like that, right?
yeah. So the how do I summarize that? Mass question is like in my early testing.
We saw something where it was directly related to that, and like it actually went a lot slower without the delay. Am I misremembering that?
No, you're remembering the correct thing, but I don't know exactly how to present what we found out. But it was without, even with the delay, like if you don't have enough threads to fill an LWB block, if you have a 128K block and you only, I was doing AK writes, so you need 15K AK writes will fit in 128K. So like when I was running with 16 threads, 15 of those AK threads would wind up in one ZIL block, 128K. And then there's one straggler thread that would, because of like metadata accounting in the block, would wind up in the next one. So instead of having all 16 fit in a single block, we would have to use 2 blocks. So there was kind of like a performance kind of cliff spike, and that could be an artifact of my testing or whatever you want to call it.
Actually, quick question about the flushes, because
Sure.
I know we make a lot of flushes, and have you tried to like turn them off to compare to see what's the impact of that? The reason I'm asking is, for instance, if it would be possible to batch up some of the flushes, since you're like we know like we had 2 IOs issued to be
Yeah.
one, and maybe somehow batch those flushes together to try to make it a little bit faster. Have you looked at that?
So the question is, did I do any performance testing about the impact of flushes? Did I try and test with flushing disabled? And could we like batch the flushes instead of issuing a flush for each LWB? Is that a good summary? I didn't do any rigorous performance testing with flushing disabled. I just used the default config. I think it would be useful to do that. The reason I didn't is because I think performance can only get better if we turn it off. So I wanted to try and see with the defaults, like, is it good enough? Do I need to do something more complicated? And since I saw a bunch of improvement with the defaults and flushing per each LWB, I kept it as is. If we needed to do testing and we found out this is doing too many flushes and degrading performance, there's no reason we couldn't change it to batch it up. But then it kind of gets us back into the batching mechanism, so we just need to be a little bit careful about how we implement that.
So I was trying to understand what the motivation might have been for the original implementation with the batching. I mean, was that just like a simple way to ensure that threads got notified in the correct order?
So the question is, what was the motivation of the original backing mechanism? And I guess maybe was that because it helped order the ITXs and things. I definitely can't comment on the original motivation because that was way before my time. Maybe Mark or Matt or George or somebody else can comment on like the motivation there. It's definitely a little simpler. Well, I mean, I think this mechanism is pretty simple just because it falls out with the ZIO stuff really nicely. The ordering just kind of, because it's batched, that you don't have to worry about the order of wake ups there. Everything just wakes up at the same time, so that is solved automatically. but I mean, from my perspective, it sort of felt like that was geared more towards throughput and maximizing throughput, because you issue a bunch of ITXs, assuming the batch size is really big, and then you wait for them all to complete. So I don't know. I know Oracle's done some work on this. I think the implementation is completely different, but you guys
Correct.
tried to address this. Do you want to?
So I think, yeah, motivation behind the original is hard to speculate on completely. The author of that isn't here.
Yeah.
But I think, leveraging the ZIL was not probably considered by him when he was thinking about things when he was developing his work. I think that the work we've done in this space inside of Oracle is to a similar end, which is to try to reduce those batch sizes
Yeah.
and be more thread specific about things. It's a very different model. But it was recognized by the developer eventually that this was a poor model in some ways. And there were improvements we made that were very similar in fact.
So with a smaller number of synchronous writers and slog, would you expect delay to be as much of a win? Or might the delay actually cause the synchronous writing to break down?
So take a single-threaded case. The question is, with a small number of synchronous writers and an S-log, can the delay negatively impact performance? Is that a good summary? So I think it can. Like for a single threaded case, you're basically always going to hit the delay. The way I rationalize that is hopefully single-threaded cases aren't the norm. And with a small number of threads writing with a previous code, it would, like, I saw improvements with 2 threads. I didn't see improvement with 1 thread because I would always hit the delay. But with 2 threads, the old code also wasn't good because it would almost always use at least 2 blocks. So the first thread would come in and do a ZIL commit, and it would consume 1 ZIL block. And once that writer finished, it would issue the ZIL block. So if you had 2 threads, one calls ZIL commit, it takes 1 ZIL block, issues it to disk when it's done, and then the next thread comes in, calls ZIL commit, and it has to be put into another ZIL block because there isn't a delay in that mechanism. So I think there is some concern potentially, at least to be aware of, but in my testing, I saw improvement even with 2 threads.
So if this is going to become the default index, so the question of what the trajectory of this is, I would be a little bit concerned because that use case is like, we often do see small numbers of synchronous writers. Like the wall writer, for example, in Postgres is going to be the central thing doing synchronous writing.
Sure.
We would be willing to gather data on the public cloud to actually to explore some hypotheses about
Yeah.
how frequently we end up with concurrent synchronous writers. Because it would be very important to us that we not do harm in the slog case, the small number of
Yeah.
synchronous writers. Because those synchronous writers will corrupt the entire system, and when they're delayed, the entire system will be delayed behind.
Yeah, so the more concern about small number of sync writers. Sync writers are important, and we don't want to delay them any more than we need to. We could set it to 0, or we could make the delay make it optionable. We did make it a percentage, so it's still 5%. You could end up adding that latency for no good reason. But yeah, if you want to, let's collaborate and figure out the right thing to do. I didn't have data to kind of test that, so I didn't want to go making wild, code changes and complicating things without, useful measurements to prove that it's the right thing to do. So.
Last question?
Having the ability to have more data sets to work, will that require more space, storage-wise? And I'm using the SUSE RAM, and it has an 8 gigabyte of capacity. Will I somehow go to that roof, you think, if I'm using the S-Log? Still, as a device?
No, repeat the question again.
It's about how much space you're going to use for the ZIL.
Yeah.
Yeah, right. The question, I guess the concern is that maybe these changes increases the space consumed by ZIL writes, right? Is that, I didn't change any of that. So in theory, it should be the same, if not improved. But let's take some measurements. If you see differently, then let's fix it.
I think there's many other improvements which can be made for the actual size used by the ZIL. Like the current mechanism is not the best for the sizing.
That was another consideration about the 5% timeout, where like without it, in my testing I was seeing these LWB blocks not utilized very well because new ITX would come in and have to get a new ZIL block. So I saw the space efficiency. The performance issue is kind of a variation on the space utilization. We want to make sure, as best as possible, we issue these LWBs as soon as possible, and we also utilize them so we don't waste space on these small, expensive devices. So, yeah, and IOPS, yeah. So, it shouldn't affect it, but let me know if it does.